Okay, this is uh, this is the lesson on vectors. We've used vectors in kinematics already. When an object goes to the right, and we know sometimes it goes to the left. If it goes to the right, we can say its velocity is positive. We put that in the equations, or forward, we can say positive. But if the object is going to the left or going backwards, we have put a negative in those for those magnitudes in the equation. But today we want to look at a situation. What if a velocity is not to the right or to the left, but up at some angle, some direction like this, some angle, and we, so any angle theta, some angle up here. And it has some magnitude, I don't know, maybe 10 meters per second of velocity, let's say. Um, when it comes to using our equations, we can't use this magnitude in the equations. We have to kind of turn this vector into something we call components. And so that's what today's lesson is about, is how do you take a vector and turn it into components? I'll explain what those are in just a moment. And we want to do the opposite, which is go from components back to the vector. And you all know velocity. And today's notation, if we're talking about a vector where you need to put a little arrow going to the right above the letter there. But of course, we also have acceleration is a vector. On your assignment, you'll have electric field, which is a vector. And, oh gosh, we could even have momentum is a vector. And so there's, again, just different kinds of vectors, but we're going to look at how to turn any of them into components. So today, this is our goal, or in this lesson, I should say, this is our goal. Given the magnitude and direction, we find the components of the vector. Magnitude is what this is, and of course the direction is going to be the angle. We typically draw the vector proportional with this number, so this is 10, and we're going to draw something that's 20, it would be twice as long, that sort of thing. We don't strictly always do that, but that's the idea. And given the components of a vector, we want to get the magnitude and direction. So let's talk about components real quick. Ah, let me talk real quick about the direction. The direction will typically be given as an angle measured from the positive x-axis. So here's your coordinate system. And if there is a vector off in this direction, then from the positive axis, we would measure an angle. It would be some angle there. Let's use this one. No, that looks the same. Okay, it's not that important. But let's use another example here. What if it's going off in this direction? Whoops. What if it's going off in this direction? Again, now here we would not use this angle. We would use an angle from the positive x-axis. So this would be our angle theta for that vector. And of course, if we're down here, we would have an angle here from the positive x-axis. Typically in the fourth quadrant, we would have an angle measured from the positive x-axis, but it would be going in the opposite direction here. And typically this angle will be negative if we're going in this, if we're going this way. Okay. So we'll get to that when we do some examples. Let's talk about components. Suppose you have Superman, and this is Superman, flying up and to the right at a velocity of 140 meters per second at an angle of 42 degrees with, the horizontal. You could ask two questions that kind of convey what the components of a vector are. how fast is Superman's shadow? And for this, we're supposing that the sun is directly overhead, so that Superman has a shadow directly beneath him. Yeah, we can use black here. So here is Superman's shadow. And so if Superman is going at the speed at that angle, Superman's shadow will have a velocity, or yeah, velocity. It'll have a speed going this way. And what this ends up becoming, what we're going to be using today, is this. This is the vector that represents Superman's shadow, the velocity of Superman's shadow, which today we'll call Vx. And it starts from the same place as this vector, and it goes all the way horizontally, all the way underneath the end of that vector here, and it stops. So geometrically speaking, what we're going to be making here is a triangle. And so if you know your trig, you can take the 140 meters per second, the angle here, and you can figure out the length of this vector, which would be the magnitude of the horizontal component, which would be how fast the shadow is moving. We could also figure out this component. So we would draw it straight up. This would be called Vy. And what this number represents is how fast Superman's altitude is rising, or how fast it's increasing. Okay, and so we're going to calculate this here just shortly. And what we've made here is a right triangle, and so we can use trigonometry to figure out these magnitudes. A little bit on notation. If we're representing a vector, we use a small arrow over the variable pointing to the right to indicate that it's a vector quantity. So I have an example down here. The velocity vector, we have to have the arrow, is 140 meters per second, and here is the direction, 42 degrees. If we use the same variable without the little arrow, it's just the magnitude. There's just no direction there. Okay. Real quick review of trigonometry. We have cosine of theta. You might remember SOHCAHTOA. That's SO, ka, toa. It's supposed to help you remember your formulas, your trig formulas. But here's our triangle, right triangle. Here's angle theta. And from this angle theta, this would be the opposite side here. So we have O. This would be the side that is next to the angle. This is called adjacent. And this is the longest part of that right triangle, which we call the hypotenuse H. And so here are your trig functions. And so hopefully you remember how to use those. We're going to practice with them right now. So let's come back and let's steal this. I'm going to plop it right here. What we want to do is we want to find the component Vx and the component Vy for Superman. And so for Vx, notice that this is the adjacent side. So what we want is a trig function that has adjacent in it. And here is adjacent, and here is adjacent. For Vy, we want the opposite side of the triangle, and so it's here, and it's also here. Now what's convenient in this triangle, the one we're looking at here, is we have the hypotenuse. So I'm just going to say right now that we're not going to erase this, but we don't want to use tangent at the moment. We will use it later. So for Vx, we're going to be using cosine. So cosine of theta is adjacent over the hypotenuse. Let's plug in what we're actually working with here. So the cosine of that angle is the adjacent side Vx over the hypotenuse, which is v. Just the magnitude of that, of Superman's velocity. Now, if we rearrange this for Vx, we get Vx equals V cosine, V times cosine of theta, right? If we multiply both sides by V, that's Vx, okay. For Vy, we'll use sine theta, which is the opposite over the hypotenuse. For this triangle, for the physics here, opposite is Vy, and the hypotenuse is V. And so we can rearrange this for Vy. Vy is equal to V sine theta. So you don't always have to, we're not always going to derive this equation, but these you kind of want to like memorize. But keep in mind that if this is not a velocity vector, let's say it's an acceleration vector, then we might be wanting, you know, the horizontal component of some acceleration, or maybe the vertical component of the acceleration. And so your equations would change to look something like this. Okay, and if it's a electric field vector, you know, then it would look like this: cosine theta and E sine theta. You know, if you have an electric field, you know, at some angle theta, or if you have some acceleration at some angle theta. Right, so this equation changes depending on what kind of vector you're looking at. So you can you memorize them, but it may look different whenever you use it, depending on your vector. Cool. Well, let's solve it now. So Vx is equal to V, that's 140, times the cosine of the angle 42. I'm just gonna write these out first I'm just gonna put them in the calculator at the same time here. Cool. Let's put these in the calculator. Very important now that I remember, you must use degree mode as opposed to radians. So it's a mode. So on your calculator, look for the mode button. And eventually you should find something that says DEG or RAD. Okay, we want this selected. We don't want radians or gradians for that matter. Make sure it's degrees. Cool, let's calculate this. 140 cosine 42. I'm getting 104. Yeah, 104 meters per second. And let's do 140 sine 42, 93.7 meters per second. So Superman's shadow has a velocity of 104 meters per second, and Superman's altimeter increases at 93.7 meters every second. So that's just an example of components. Okay. What you want to remember are these, or how you write those depending on your vector. The units of components are the same units as your vector. Cool. Let's try a real example. Let's take a vector, it's a force vector of 18 newtons at 170 degrees. And the way you would solve this is first you would draw this vector. So we'll need a coordinate system. And when we draw the vector, we'll start with the force vector in the correct direction. Then we will trace or draw the x component. And as if you didn't lift up your pen, then we would continue drawing the y component. Make sure that all of your lines are arrows and that your angle is from the positive x-axis. So let's draw a coordinate system. 18 newtons, okay, but it's at 170 degrees, which is about right here. This would be 170 degrees. This is our force vector. Now let's draw our components. I'm doing them in different colors. Obviously, you don't have to do that. And you never will. I'm just doing this we start from the same place here. I'm just doing this so you can visualize. This is the x component. And as if I did not lift up my pen, I'm going to draw the y component. Draw everything as arrows. Oh, let's label it. Draw everything as arrows. Okay, the vector starts from the origin, and your component, your fx, your horizontal component, starts from the origin as well. And we go this way. So your two components will touch from head to tail, and they will end up at the same location as your original vector. Cool, and then the angle. So this all looks good. Now we just need to calculate them. So fx is f, the magnitude of f, times the cosine of theta. So that's 18 newtons times cosine of 170. 18 cosine 170. And I'm going to go ahead and do the y component as well, but we will write it first. So this is negative 17.7 newtons, which makes a lot of sense because negative, it's going to the left here. The negative x direction. That's our component. Let's do the y component. This is f sine theta, which is 18 sine 170, which comes out to 3.12 newtons. Which is clear here. We're going in the positive y direction, so positive. Well, that's it. When you draw your picture, well, besides drawing it correctly, make sure everything is labeled here. Cool. Example 2. Now let's suppose we have two components and we want to get the vector out of this. We want to go from the components to the vector. We'll do the same thing. We want to draw a sketch of this. And starting from the origin, I'm going to draw my x. Now it's positive 8 meters per second squared. So I'm going to go this way, about right here. This is ax. And as if I did not lift up my pen, I'm going to go and draw the vertical component, negative 6. So that's in the negative y direction. And not proportional, but trying to make it look like it is. If this is 8, then I'm going to say this is about 6. Yeah, somewhere right here. This is the vertical component. The vector also starts from the origin, and it meets up with this one. Let's label it. It's the a vector. And of course, this is the angle theta. Cool. So how do we get the magnitude of the acceleration vector? Remember, we're going from components now. We want to get something that looks like this, with a magnitude and a direction. But in this case, for the acceleration. Well, this makes a right triangle. This is the right triangle. And if you know both sides of your right triangle, you can figure out the hypotenuse. Right? A squared plus b squared equals c squared, although I'm going to write it like this. A squared, and by that I mean my acceleration vector, is ax squared, let's write that again, plus ay squared. Sometimes I'll just do it like this, because we're going to end up doing that anyway. But I'm just doing an example here. So I think ax was 8, and ay was -6. Now when you put these in, get in the habit of writing them in parentheses, because you should not get a negative, or -6 squared, you should not get a negative value for that once you resolve that. So let's do 8 squared, and in parentheses -6, close parentheses, and then square it. Okay, so keep in mind that this is different. So don't do that. And so I get 100. And square root of 100, this gives us A, is 10. The units are meters per second squared. Don't box that in because that's not our answer yet. Now we need to know the direction of the acceleration. The direction of the acceleration. But I'm noticing something here. If this is theta, this is opposite, and this is adjacent. And so I'm remembering my trig functions, that tangent of theta is opposite over adjacent, or the tangent of theta is ay over ax. And so we can solve this for theta. Here, theta is essentially isolated, but we just need to get rid of the tangent. And so that's tangent inverse, or arctangent. And what I remember is that, sine -1 of opposite over hypotenuse, and cosine -1 of adjacent over hypotenuse, and tangent -1 of opposite over adjacent gives you an angle. These will give you an angle. So, well, that worked out really well. Let's do that. So anyway, theta is equal to the inverse tangent of ay over ax. And this is what you want to remember. Whoops, let's not box that in. Oops. This is what you want to remember. And I never need to see this over here anymore. We just want to go straight from here. So let's do that. Tangent, -1. Inverse tangent or arctangent, however you want to call it. I call it inverse tangent. Ay was -6 and ax was 8. Oops. Just typing this in the calculator. I get an angle of -36.9 degrees, which makes a lot of sense because from the positive x-axis we go in this direction, that would be a negative angle. Again, don't box it in, that's not the final answer. our final answer is the acceleration vector is equal to 10 meters per second squared, comma, the angle negative 36.9 degrees. This is the vector notation. This is our full vector here with magnitude and direction, not just in parts like this. Cool. On your assignment, you have some, let's see here. In going from components to a vector, you have some answers, some vectors that end up in, let's see, this is 1, this is quadrant 1, this is quadrant 2, this is 3, and this is 4. Your calculator, um, when you do this part, when you find the direction, your calculator always gives you an angle that's in the first quadrant or in the fourth quadrant. And so if your answer is a vector that's in this quadrant, what it'll probably do is really give you an angle here, some negative number. What you need to do is add 180 to it. So what I'm saying is if your vector is in the second quadrant, you will add 180 to your calculator. And actually also for the third quadrant, if your answer is in the third quadrant, it would probably give you this angle here. So again, add 180 to it um, to get the correct answer. And just double check. I mean, draw your sketch. And like here, does negative 36.9 make sense? Yeah, but if I know my vector had a negative x component and a positive y component, and so therefore I know my vector needs to be over here, but they gave me a negative angle, just thinking it's like, okay, I'm going to correct this by adding 180 uh, to my calculator's answer. So just double check your work. And I think that's it.